Alright, in this video I'll be explaining Shigley problem 4-98 that was assigned for homework in my MAE 3323 class, Tulsa Fall semester 2012. And this is a cantilever beam with a uniformly distributed load and a point support located at point B. And this point support makes it an independent, indeterminate structure. Excuse me. And so the question is, what is the reaction at point B, and what are the reactions at the wall? We're not actually going to calculate a deflection here. If we wanted a deflection, we'd take the next step and add a dummy load Q wherever we want to do the deflection. And so, using Castigliano, I would choose to treat this support as the indeterminate reaction and replace this support with an upward pointing RB, reaction at point B. And so my intent is to measure X from the left, advancing to the right, and anytime I want the moment, I will make my cut and look left. So I don't actually need to do any statics at the wall yet. In the end, I'll have to do some statics at the wall. And so I will have my energy terms divided into two regions from A to B and a region from B to C. And so I will set up my moment number 1 in region A to B. And that moment is simply a Wx squared over 2. And maybe may need to separate that just a little bit. Let me see if I can just move things up a little bit. Let's see what I've got. Yeah, now we can see that Wx squared over 2 better. So the moment's Wx squared over 2. I'm wanting to determine the load in indeterminate reaction RB. So I'm going to take my partials with respect to RB. So I can set that deflection equal to 0 and solve for that load. So the derivative of moment number 1 with respect to RB is 0. So I get no effect from this term when I multiply these two together, so I won't even bother writing that integral piece. In region 2, from B to C, my moment is still Wx squared over 2, and I'm going to call that the positive moment, and then therefore the moment due to B is negative, so minus the reaction at point B times the distance x minus a when I get into this region out beyond a. And the derivative of moment number 2 with respect to RB is a minus x minus a quantity. Here it is. And just for fun, I am printing out the product of these two terms. And here it is. And RB is not a dummy load. It's not going to go to 0, so I don't set it equal to 0. I leave it in here. We could expand this out, then it would make it easier to do the integral. I'm going to let MathCAD do the algebraic expansion, and then I'll let MathCAD integrate this thing. But it looks like we're going to have an x term here and an x squared term there, which is going to give us an x cubed. So we integrate, we're going to get x to the 4th kind of things. So my deflection at the location of load RB in the direction of RB is an integral from A to L, from the distance A all the way to the distance L, which is my region BC. Okay, so integral over that region of the moment in region 2 times the partial of moment 2 with respect to RB over EI. MathCAD does the substitution, MathCAD does the integration, MathCAD substitutes in the limits, plugging in L and then subtracting the same quantity with A plugged in. And here is everything. So this is our deflection at the location of the load RB as a function of RB and everything else. Now, we know that deflection is 0, so that's how we're going to solve for the value of RB. So in MathCAD lingo, the value of RB is this deflection term set equal to 0. And then we go inside and we solve for the RB value. So deflection term set equal to 0, solve it for RB, simplify it a little bit, and here's our deflection term. And if you look carefully, this matches the solution given by the author in the solution manual, but the author only presented the superposition solution. The author didn't present the Castigliano solution. So here I am presenting the Castigliano solution. If you want the Castigliano solution, simply print, just pause this thing and print this image. So I have my reaction at point B because of that indeterminate reaction. Now I'm going to do statics and solve for the reactions at the wall. By summing forces in the y direction, I have RB plus RC minus W times L. I'm going to set that equal to 0 and solve for RC from this. It'll do the algebraic substitution of this stuff right here, plug it in for RB, and then it will do the substitution. It'll solve for RC. It'll simplify it. Here's the answer, which matches the author's solution manual answer very nicely. And then finally, the last term is summing moments about point C, which will then involve the RB, and it'll involve the WL squared over 2 term and the unknown moment at point C. Set all of that equal to 0 and solve this equation for the moment at C. Again, MathCAD will go back and grab the RB definition and plug it in right here and include all of that. And so here is the value of MC. Actually, it's changed on me a little bit because earlier it was showing me W over 8 times each of these terms, but we can extract the W over 8 and match what the author has. Now, here is the author solution. We are going to choose this RB as unknown. And so what we're going to look for is a superposition of a cantilevered beam with a distributed load and a cantilevered beam with a load which is not at the end. And so the superposition of those two equations, if we go look up in the back of the book, and I have not, the superposition of those two deflections would be here, okay? And this would be the deflection at the location of, at location x equal a, which is the location where this force RB is applied. But now we're going to take the superposition deflection equation and set that equal to 0 at the, so the deflection at point B, set it equal to 0, and solve for RB. So we solve for RB, we get this term which matches the Castigliano from above, and then we do the statics to find the other two, the reaction at C and the moment, and we get the same thing that Castigliano gave us. I'll let you study those a bit more carefully, and that ends the video.